Okay, so just a little note before we continue. This is where we hit our section where we have different days off for different schools over the next couple of weeks. Boston, I really realize you guys are not in session today, so I appreciate y'all logging in from home. I believe Monday, I think Clayton, you guys are out, and then next Friday, Flambeau, you guys are off. So over this next week and a half, we're gonna kind of circle around a little bit, do a little bit of review each day, to help catch up for those that haven't been in session. At some point, we may coming up here. At some point, we'll have days where we won't have our class if we have enough schools out. I believe it looks like coming up like March 13th, we have a day that's like that, where two of you guys are gone on the same day. I'll keep you posted as we go. We might have a Friday before then that we do the same thing. We're required to get 32 days, 32 hours in between now and May, so we've got plenty of extra time scheduled in. So I'll let you guys know at this point, this next week and a half, we are going to have class every day, each of the days. We're just going to kind of do a little bit of review each time to catch up those that had to miss. Last class was exam 1. I have that from everybody but one student, so I'll be sending out an email probably Monday if I haven't seen that one yet. And then I'll get all those graded and back to your sites by next week, Wednesday, so you can go over those a little bit too as we need. So Unit 2, we start into more of the useful information that we have to have in order to do the dosage calculations. And one of the skills we need is some basic algebra. So we need to look at variables and how variables work. Variables actually have several functions. One, they can be used to create a rule. So that would be like a property of numbers, like our commutative property. A plus B is equal to B plus A. That's a rule. And if I'm using my variable like that, the variable can take on any value. So here, A and B, they could be 1, 2, 753, negative 18, 6.4794, the square root of 27. They can be any real value of a number can go in for those when I'm using them in that form. A second application, this is a formula. So in dosage calculations, one of the options is to use formulas. So a formula might look something like this. The administered dose is equal to the doctor's orders divided by the on-hand dose times the vehicle. Now in this case, the possible values that can go in for those variables depend on the situation. In other words, what is that formula being used for? We can't have negative amounts of medications, so none of those numbers can be negative in this case. Certain medications, we can't go over a certain dose, so we can't have those in there. For dealing with capsules or tablets, we can either deal with a whole tablet or a half tablet. Capsule, we have to deal with a whole capsule. So we're limited in our possible values by the physical constraints of the situation being described. Another use of a variable is what is called an unknown. So in an unknown, this is probably the one that you're most familiar with. This one we'll look at on Monday. Something like 3x plus 7 equals 25. Here, that variable has a value. So it already has a set value. We just don't know what it is, but we can find it. And that's what we're going to be doing with those, is finding those set values when we get to it. And then today we're going to be looking at algebraic numbers. So in algebraic numbers, the variable is the place value. Often in algebraic numbers, we hear it referred to as polynomials. And so let's look at what the variables do. We're going to look at the algebraic numbers in just a second. Let's look at what variables really do. Variables are always used in place of a number. And we're used to it being a letter, but it can actually be any symbol. The American spelling there. It can be X, Y, Z are probably the ones we're most used to using, but A, B, F, M, P, any letter can be used, but also any symbol. We can use the hashtag or the @ symbol or ampersand. Any of those symbols can be used as a variable. In fact, when we talk about angles, it's quite common for us to use Greek letters: alpha, beta, theta, gamma, phi. We often use Greek letters as our variables. Any symbol can be used in place of a number as a variable. So let's talk about algebraic numbers. Little review from our number systems. We had the place values of our whole numbers. This was the ones place, or 10 to the 0, we now know. Tens place, or 10 to the 1. Hundreds, or 10 to the 2. 10 to the third is the 1,000s. 10 to the fourth is the 10,000s. 10 to the fifth. Those place values are powers of 10. And when we had a number like 527, if we wrote that out in full form, it was 5 hundreds and 2 tens and 7 ones. Well, alternative form of writing that full form out, rather than writing out the names of the place values, we could have wrote the powers of 10. We could have wrote, instead of 500s, we could have wrote 5 times 10 squared. 2 tens, instead of 2 tens, we could write 2 times, we don't have to put the 1 on the 10, just 2 times 10, it's 2 tens. Plus, instead of writing out the 10 to the 0, we just usually write the 7, and the fact that there's no name here implies that that's the ones. Well, when I write this out in this form, it looks an awful lot like our basic polynomials, like 3x squared plus 9x plus 2. We can see that the place values now, instead of being powers of 10, are powers of x. Instead of 10 squared or hundreds, we have x squareds. Instead of tens, we have x's. We still have ones because 10 to the 0 equals 1, but x to the power of 0 also equals 1. Anything to the power of 0 equals 1. So the last digit is always the ones place, no matter what base number system we're working in. So when we look at our polynomials, it's really nothing more than base x numbers. Our number system was called a base 10 number system because the place values were exponents with bases of 10, 10 to the power of. Our algebraic numbers, base x numbers, because the place values are exponents with bases of x. It's x to the power of 2, or just x to the 1, and on down the line. So there are a lot of similarities between our algebraic numbers, or what you typically call polynomials, and our integers that we work with. And when we go to add them, we might take our 3x squared plus 9x plus 2 and add it to 5x squared plus 4x plus 7. Now, first of all, here, those parentheses are not enclosing symbols here. Remember, we said parentheses do other things. Here, the parentheses are just separating those numbers. Just like when we worked with negatives with our integers, the parentheses told us that was times a negative number, not subtracting that number. Same type of thing here. Those parentheses are telling us that we have two separate numbers that are being added together. And you've probably learned shortcuts for adding these. Most textbooks will just say, take out the parentheses and combine what they call like terms. Those just combine the terms with the same name. But the long, and that's a shortcut and it works fine. But the long form, this is just add them just like we do our whole numbers. We write out the first number, 3x squared, plus 9x plus 2. Then we write the second number underneath it, making sure we line up the place values. The 5x squared has to go under the 3x squared. The 4x's goes under the 9x's. And the positive 7 ones goes under the 2 ones. And we are adding here, so we add down the columns. 2 plus 7 is 9. It's a positive 9, so put a plus in front of it. 9x plus 4x is 13x. Again, positive, I put a plus in front of it. 3x squared plus 5x squared is 8x squared. Now here we see our first major difference between algebraic numbers and whole numbers. That's right here. If this were a whole number, we'd have to carry. Well, in algebraic numbers, there is no carrying from one digit to the next. That could be 2,458x. There is no carrying into the next digit because it doesn't have a translation that way. So that's the first big difference between our algebraic numbers and our whole numbers, is that we don't carry. The digits can have, each digit can have more than one digit in it. Each place value, I should say, can have more than one digit in it. The second big difference is when we're dealing with our integers like 258, either every digit's positive, 258 is 2 hundreds and 5 tens and 8 ones, or every digit's negative. If it was negative 258, that'd be negative 200s and negative 5 tens and negative 8 ones. Every digit is negative. But in an algebraic number, each digit is free to be positive or negative on its own. We might have 4x squared minus 8x plus 3. And we're going to add that to 2x squared plus 13x minus 9. And again, we're going to set it up, lining it up like we would whole numbers. So we recopy 4x squared, negative 8x, positive 3 ones. Put the 2x squared under the 4x squared, the positive 13x under the negative 8x, and the negative 9 ones under the positive 3 ones. And we are adding down our columns here. Now is where we have to remember how to work with our negatives, with our integers. 3 plus negative 9, well, positive 3 and negative 9, negative 6. Negative 8x and 13x. So we combine the counts. Negative 8 plus 13. Well, negative 8, positive 13, that's a positive 5. And we keep the name of x. 4x squared and 2x squared, again, we combine the counts. 4 and 2 is 6. We keep the name of x squared. So we have to be very careful with those integers. Here's a spot where it comes up to haunt us a little bit. It's even worse when we get into subtraction. If we're subtracting these algebraic numbers, we might have something like 3x squared plus 8x minus 11 minus 7x squared minus 7x plus 3. So I'm going to rewrite this, making sure I line everything up again. 3x squared plus 8x minus 11 Then we put the 7x squared under the 3x squared, the negative 7x under the 8x, and the positive 3 ones under the negative 8 ones. And we are subtracting now between these two numbers. So we have to remember now each column is subtraction. Negative 8 minus 3, or negative 11 minus 3. That becomes negative 11 plus a negative 3. So that's negative 11, negative 3 go the same direction. That's a negative 14. Remember I said subtraction with our integers is going to haunt us for the whole semester? Here's one of those spots. 8x minus a negative 7x. So combining the counts, that's 8 minus a negative 7. That's just 8 plus 7. So that's a positive 15, and we keep the name of x. 3x squared minus 7x squared. Again, we combine counts. 3 minus 7 is negative 4. Name of x squared. Now, many of you were probably shown a shortcut, and the shortcut you were shown, but there's a lot of alliteration there. What you were shown to do probably looks something like this. To take out these parentheses and distribute the negatives. You make this a plus, and then you change the sign of everything inside the parentheses. And then you combine them. 3x squared negative 7x squared gives you the negative 4x squared. Positive 8x, positive 7 gives you positive 15x. Negative 11 and negative 3 give us the negative 14. That shortcut works, but all it is just a short way of doing this longer process. Next, multiplication. So we need to work a little bit with our powers. We've done some, and we'll do more as we go on. But something like x to the power of 3, we know that is x times x times x. Just 3 x's multiplied together. So if I had x to the power of 3 times x to the power of 5, x to the third is 3 x's multiplied together. X to the fifth is 5 x's multiplied together. If I multiply those all together, I have 1, 2, 3, 4, 5, 6, 7, 8 x's multiplied together. That's x to the 8th. Now I'm not going to go real deep into developing this concept because most have already been taught that when you are multiplying exponents with the same base, you add the powers. 3 plus 5 is 8. So I'm multiplying exponents with the same base. Both of these have a base of x. I add the powers. The 3 plus 5 give me the 8. So if I have x to the 18th times x to the 35th, that's just going to be x to the power of 18 plus 35 is 53. So x to the power of 53. You do have to be careful, though, because if I have x to the 7th times y to the 5th, that result is just x to the 7th, y to the 5th. These do not have the same base. One has a base of x, the other has a base of y, so we can't combine the powers. We can't add the powers there. They have to stay separate. If I put numbers in with those variables then, like 9x to the 5th times 3x to the 3rd, just like with any other form of a number, we have to combine the counts. We do 9 times 3 is 27. And then we also combine the names. X to the 5th times x to the 3rd. When we're multiplying exponents with the same base, both of these have a base of x, we add the powers. 5 plus 3 is 8, x to the 8th. What if we have multiple variables, multiple names, if you want to call them that? 4 x to the 7th, y to the 3rd, times 8 x to the 5th, y to the 4th. Well, we combine the counts. 4 times 8 is 32. And then we combine each of the names separately. X to the 5th times, or x to the 7th times x to the 5th. That is x to the, when we're multiplying, we add powers, so 7 plus 5 is 12. Y to the 3rd times y to the 4th is y to the plus 4 is 7. So 32x squared y to the 7th. I'm not going to waste a lot of time multiplying single digit numbers like this. We're going to look at the next step. When we were multiplying things like 4 times 32, what we did with whole numbers looked like this. We put the number with the most digits on top and times 4. 4 times 2 is 8. 4 times 3 is 12. Carry the 1. 128. So when we work with our algebraic numbers, if we have something like 5x times 7x minus 3, we can do the exact same process. We write the number with the most digits, the 7x minus 3 on top, times the 5x on bottom. Then we do 5x times negative 3, that's negative 15x. 5x times 7x, 5 times 7 is 35. Also combine the names though, x times x is x squared. Exactly the same as our process of multiplying whole numbers up here. But remember we said in that second day that there are other ways of adding numbers and subtracting numbers other than what we've seen. I showed you a method where we started on the left and worked to the right. There are also other methods for multiplying numbers. 4 times 32, rather than doing it like this, that's what the way we've all been taught, we could have done this. Write it out in the long form. 4 ones times 3 tens and 2 ones. And then it's called distributing. 4 ones times 3 tens is 12 tens. That gets split into 100 and 2 tens. 4 ones times 2 ones is 8. Ones times ones is ones. So 128. Exactly the same answer we got before. But this process looks longer and more algebraic. The other process was what's shorter. With algebraic numbers, 5x times 7x minus 3, this is the method that most of us have been taught to use. And we call it distributing. Where we take the 5x and we multiply the 7x, 35, x squared. Then we take the 5x times, remember this is a negative 3. An operation always operates on the number coming after it. So 5x times negative 3 is a negative 15x. Again, that's exactly what we got up above here. It's just a much different process. It looks different. So we can use the exact same processes with our algebraic numbers as we can with our whole numbers. If I had two multiple digit numbers being multiplied together, 8x plus, oops, that's wrong. Let's go to whole numbers here. 34 times 25. Well, I could set it up as 3 tens, 4 ones, times 2 tens, and 5 ones. This is the process we've all been taught, only I wrote the numbers out in long form. So 5 times 4 is 20. Ones times ones is ones. Well, I'm going to keep the 0 ones, and I'm going to carry the 2 tens. 5 times 3 tens, 5 times 3 is 15, plus the other 2 is 17 tens. Again, I keep the 7 tens, and I carry the 1 into the hundreds. Then I move over to the 2 tens. 2 tens times 4 ones, 2 times 4 is 8. Tens times ones is tens. This is why we've always been taught to put in a 0 down here, is to line those up. 2 tens times 3 tens, 2 times 3 is 6. Tens times tens is hundreds. And now we go ahead and add. 0 and 0 is 0 ones. 7 and 8 is 15, so 5 tens. Carry another 100. 1, 1, and 6 is 8 hundreds. So that gives us 850 as that result. When we work with algebraic numbers, 7x plus 5 times 2x minus 3, we can use the exact same process. 7x plus 5, 2x minus 3, and we're multiplying. Negative 3 times 5 is negative 15. Negative 3 times 7x is negative 21x. Move over to the next digit. 2x times 5 is a positive 10x. 2x times 7x is 14x squared. Now we can combine. We've got the negative 15. Negative 21x and positive 10x is a negative 11x and 14x squared. Now this process is what we used for whole numbers, but not what most of us were taught for variables. There's an alternate process for whole numbers. What was this? 34 plus 20 times 25. Where we wrote them out, again, long form, 3 tens and 4 ones times 2 tens and 5 ones. Where we did 3 tens times 2 tens is 6 hundreds. 3 tens times 5 ones is 15 ones. So that's going to be 3 tens times 5 ones is 15 tens. So I'm going to keep the 5 tens and carry the 100. Then we move here. 4 tens times 2 tens. 4 times 2 is 8. That is 8 tens. 4 ones times 5 ones is 21. So we keep the 0 ones and carry the 2 tens. And then we add them up. We've got 0 ones, 15 tens, so we keep the 5 tens, carry the 1 into the hundreds. 1, 6, and 1 is 8 hundreds. So we get 850 just like we did up above. Well, this is a lot longer process. Well, some of you may have recognized this process as your algebraic process that you learned called FOIL. F-O-I-L, first, outside, inside, last. And when we did our algebraic numbers, 7x plus 5 times 2x minus 3, that FOIL is what most of us were taught to use. First, F stood for first, we multiplied the first numbers. 7x plus 2x is 14x squared. O stood for outside or outer, we multiplied the outside numbers. 7x times negative 3 is a negative 21x. I stood for inside or inner. We multiply the inside numbers. 5 times 2x is a positive 10x. And L stood for last. We multiply the last numbers. 5 times negative 3 is a negative 15. And then we combine. We've got the negative 15, negative 21, and positive 10 is a negative 11x and 14x squared. So 14x squared minus 11x minus 15, exactly what we got over here. The FOIL method works better for our polynomials or our algebraic numbers, because in the algebraic numbers we don't have to carry. For the whole numbers we use this vertical method like this because we have to do that carrying. And so with the FOIL method, when we have to carry, it gets kind of ugly, kind of sloppy. So the process for working with whole numbers and algebraic numbers, we can use the same processes. It's just sometimes with different forms of numbers, one process works better with that form than others. FOIL works with whole numbers, it just gets sloppy because of the carrying. So we tend to use that vertical method with the whole numbers. With algebraic numbers, the vertical method works just fine, it's just a little bit more writing to get it written out. The FOIL method, we can work on it right in place. So we tend to use the FOIL method for our algebraic numbers or the polynomials. We can divide. If I have x to the 6th divided by x squared, remember x to the 6th, 6 x's multiplied together. X squared is 2 x's multiplied together. And remember, we've talked about fractions and division problems being kind of interchangeable. So I can turn this division into a fraction and then cancel out, reduce the numerator and denominator. Divide out an x and another x. What's left on bottom is just a 1. On top, we have 4 x's multiplied together, or just x to the 4th. That result is x to the 4th. Again, I'm not going to do a lot more time of developing this concept. Most of you have seen that when you have exponents with the same base, again, both of these have a base of x. When you divide, you subtract the powers. 6 minus 2 is 4. So if I have x to the 25th divided by x to the 11th, they both have the same base, which is x. 25 minus 11 will be 14, so it's x to the 14th. So if I have numbers involved, 28x to the 7th divided by 4, x to the 4th, I divide the counts. 28 divided by 4, this is just a normal division of 7. Then I combine the names. X to the 7th divided by x to the 4th. Again, they have the same base of x, so I can subtract the power. 7 minus 4 is 3. If we have a multiple digit number divided by a single digit number, we might have 846 divided by 2. We can write that out as 8 hundreds and 4 tens and 6 ones, and divide by 2 ones. And we can divide each digit separately. 8 hundreds divided by 2 ones, that's 4. Hundreds divided by tens is still hundreds. Hundreds divided by ones is still hundreds, I should say. 4 tens divided by 2 ones. 4 divided by 2 is 2. Tens divided by ones is still tens. And 6 ones divided by 2 ones. 6 divided by 2 is 3. Ones divided by ones is ones. 423 we get. Now again, most of us haven't seen it written out in that full form or long form like that. But when we get to algebraic numbers, that's exactly how we do it. We might have 12 x to the 5th minus 20 x to the 3rd plus 16 x squared divided by 4x squared. We divide each digit. 12x to the 5th divided by 4x squared. 12 divided by 4 is 3. X to the 5th divided by 4. Again, they have the same base of x, so we subtract the powers. 5 minus 2 is 3, so that's x to the 3rd. Next digit, negative 20x to the 3rd divided by 4x squared. Negative 20 divided by 4 is negative 5. X to the 3rd divided by x squared. 3 minus 2 is 1, so it's x to the 1, or just x. 16x squared divided by 4x squared. 16 divided by 4 is positive 4. X squared divided by x squared cancels out. We are not going to do multiple digit division by multiple digit numbers. Things like 2x minus 3 going into 5x to the 4th minus 12x to the 3rd plus. We're not going to get into that. We'll save that for your college algebra classes or pre-algebra classes. We don't need that type of correlation in this class for the medical math that we're going to do. We will, however, go on to the next step. The next step is going to be that unknown. That is where we had things like 3x plus 7 equals 25. And we would solve for x. This is where we're going to pick up on Monday. Now, right now, I know I'm cutting it a little short today, but with Mawston out, I know a couple of them said they had to work today, so they couldn't come in. So we're going to cut it off there. Very unlike me, but I'm also not going to have any homework today. Now, I will have the course videos posted by the end of the day tomorrow, hopefully. So for next week, like I said, Clayton, you're out on Monday. So I will record that lecture and have it posted for you so you can see it on Blackboard. If you don't know how to access Blackboard, let me know and I can just send you a direct link. Send me an email and I can send you a direct link. Same Flambeau, I think you're out next Friday. So the same thing will be true there. Just let me know and I can send you the link, or you can get the link off Blackboard. I'll also make sure we give you the homework ahead of time. For Monday, just for Clayton, let me grab, it's going to be page 49 through 50. Solving equations.